Hi everyone, welcome to the interview series episode 2. Today the topic is evaluation metrics on regression problem. Today we have Radha with us to answer all our questions. Ready Radha?
Hi Deepthi, yeah, I am ready. What questions you have for me today?
A lot of questions and we are going to gain a lot of knowledge from you today. So let's get started. The first question. What is a regression problem?
So, a regression problem is a machine learning problem where the target variable is a continuous variable. It's not discrete, it is a continuous thing.
So if it's a discrete, it's a classification problem. So it's a continuous variable. So it's a regression problem. Great. So
Yes.
let's tell me a few metrics for linear regression.
So, some of the metrics which are used for evaluation for regression problems are mean squared error, RMSE, and R2 square.
Okay. So let's start with MSc. What is MSc?
So mean squared error or MSE measures the average square difference between the estimated values and the true values.
Okay, what's the formula?
So its formula can be given by 1 by n sigma j equal to 1 to n yj minus y hat j square, where 1 is the actual value and the other is the estimated value.
Okay, great. So is there any limitations for this metric?
Yes, there is one limitation for MSC that it penalizes even a small error, which leads to overestimation of how bad the model is, and it's also sensitive to outliers.
Yes. So even a small error is penalized. It means a larger error will be much more larger because of the
Yes.
square. Correct. So is there any better metric which overcomes this limitation?
So another metric is there. It is called root mean squared error RMSE. It is the square root of the average square differences between the predicted and the observed outcomes. So its formula is RMSE is equal to the square root of predicted minus actual whole square divided by n, since it's the average.
Okay, there's a root over here. That's the difference. Okay.
Yeah.
So what is the difference between these MSc and RMSc?
So generally RMSE is preferred over MSE because it is in the same unit as the target variable. This makes it easier to interpret and understand the magnitude of error. While both of them are sensitive to outlier due to the square root operation, RMSE is a bit less sensitive than MSE. So MSE has some desired mathematical properties, that is, it is differentiable and hence can optimize better. So it's used as a loss function, but often RMSE is preferred for model evaluation due to its interpretability.
So the MSc is for loss function, it's used, and RMSc is as an evaluation metric.
Yes.
Great. So there is one more metric called mean absolute error. What is it?
So mean absolute error is the average of the absolute difference between the predicted and actual values. So this is used when outliers are not a very big concern.
So this will ignore the outliers basically.
Yes.
So if you're having a use case where you want to ignore outliers, then this is a better metric. But in case you want to
Yes.
consider outliers, then it's not a good metric.
Mhm.
Great. So what is coefficient of determination?
So coefficient of determination is also called as R square. It is a metric used for evaluating the performance of a regression model. This metric helps us to compare one model with a constant baseline and tells us how much our model is better than the baseline model. So first, then what is baseline? Baseline is the constant line passing through the mean of all the actual values. So its formula can be given by 1 minus mean square error of the model by mean square error of the baseline.
Okay, great. So how do you interpret this R square value?
So if R square is greater than 0, it means it's better than the baseline model. If it's less than 0, it indicates that the model is worse than baseline. If the model is close to 1, it indicates that the model is a good fit for the data. R square is always less than or equal to 1.
Okay, so you mean R square can be negative as well.
Yes.
So if it's negative, it means it's worse than the baseline. Oh,
Yes,
nice.
it's negative.
But it cannot cross 1. Great.
Yes, because it's 1 minus MSE of model by MSE of baseline. So maximum value is 1 only.
1. Correct, correct. So are there any downsides of this R squared metric?
Yes, there are a couple of downsides. That is like R square always increases when there are more features added to the model. Even if the features are not statistically significant, the R square keeps on increasing. That is one big problem of R square.
Okay, okay. So can you explain a bit more about adjusted R square?
Yes, the adjusted R square will only increase if the new feature actually improves the model's accuracy.
Mm.
Adjusted R square is always lower than R square as it adjusts for the increasing features and only shows improvement if there is a real improvement. So it can be
Okay.
given by the formula 1 minus n minus 1 divided by n minus k minus 1 into 1 minus r square. So where n is the number of observation, k is the number of independent variables, ra square is the adjusted r square.
So from the formula, it's very clear that adjusted R square is always less than R square. So
Yes.
as a summary, what we can say is for a simple linear regression where you have a single feature, more or less R square and adjusted R square will give you more or less similar value. But if you are going for multiple linear regression, like say you have more than one feature, then adjusted R square helps, right?
Yes, exactly.
Great, great. So this is an end of I mean there are I mean this is the end of various metrics for linear regression, but there is another type of regression that is forecasting. So especially
Yes.
the time series forecasting. So
Yes.
there are few metrics for time series forecasting as well. Can you elaborate more on those?
So the common evaluation metrics for time series forecasting include MAPE and WMAPE.
Okay.
So
Can you explain what is MAPE?
MAPE stands for mean absolute percentage error. It is a metric used to evaluate the accuracy of a forecasting model, but predominantly it's used for time series forecasting. Its
Mm.
formula is given by sigma I equal to 1 to n AI minus PI divided by AI into 100, and this is averaged out divided by n.
And okay. So how do you interpret these values?
So MAPE tells the average deviation from the actual. The deviation can be either on the positive side or on the negative side. For example, if MAPE is 5%, it means the predictions are 5% away from the actual. It could be either on the lower side or upper side. So, lower the MAPE, better the values.
Okay, lower the MAP, better the model. Correct.
Yeah.
So, are there any downsides of this particular metric, MAP?
Yes, there are a few limitations for MAPE. Firstly, the actual values cannot be zero because as we saw in the formula, there is a AI actual value in the denominator. So they can't be zero because it will be undefined. And secondly, if the data has a lot of variability, MAPE is not the ideal metric because it gives equal importance to all the values, irrespective of the magnitude of actual values, which leads to
Okay.
incorrect evaluation. And the
Hmm.
third thing is MAP can never be used if the actual values are negative.
Okay, okay. If it's a negative, then it just cancels out, I guess, because of
Yeah.
which it will lead to incorrect evaluation.
Yes.
Mhm. Okay. Then, is there any other metric that would overcome these limitations?
So there is a variation of MAPE which is called as WMAPE, which overcomes the first two limitations, that is variability and the zero and near zero values of actual. But the third limitation, that is when actual values are negative, that still stands a limitation for WMAPE.
Okay, so the third limitation, we don't have any metric that would overcome the third limitation, but the first two limitations are
Yes.
overcome by
Yes.
WMAP. Okay, great. So how is the WMAP overcoming these limitations? Can you explain it?
Yes. So WMAPE stands for weighted MAPE, and its formula is sigma I equal to 1 to n AI minus PI by sigma I equal to 1 to n AI into 100. Since there is the actual values are not in the denominator now, it is able to overcome the first limitation, that is the zero or near zero values limitation. And the
Mm.
second thing is, since it's a weighted average, it gives importance to higher actual values, and the variability assumption limitation is also removed.
Okay, okay. Great. So finally, for simple linear regression, we can go with R square or RMSE. If you wanted a relative measure, then it's better to go with R square. If not, then RMSE is also good metric. And if it's for multiple linear regression, then it's better to go with adjusted R square. And if it's a forecasting problem, especially time series forecasting, then you have to go with WMAP. But always remember, if you're working on a forecast time series forecasting, your values cannot be negative if you wanted to use a WMAP as a metric. Right?
Exactly.
Okay, that's a great session, Radha. We have learned a lot from you. Thank you so much. And this is the end of the session, guys. Thank you so much. See you in the next video.
Happy learning, everyone. Thank you.